actually the thing down there.
Hello everyone, my name is Yu-Wei too, and the topic of my talk is Monte Carlo integration and variance reduction methods. And this is the outline of my talk. The part 1 I will talk about Monte Carlo integration, and part 2 is about variance reduction method. And finally, I will give a short conclusion of my talk. Let's see part 1, Monte Carlo integration. Assume x is a random variable and f is a function. Then how do we compute the expectation of fx? We have 3 methods. First one, we can consider just calculate the integral analytically, just use calculate integral fx by x dx. And then the second method, we can consider use numerical integration to solve the integral. Or we can consider using Monte Carlo integration, which I will introduce later. By law of large number, we have 1 over n summation I from 1 to n fxi tend to expectation of fxi as n tend to infinity. So we can use this approximation, and 1 over n summation I from 1 to n fxi will tend to expectation of fx. So we can use this approximation to derive the integral of fx by x dx when n is large. Then this is the Monte Carlo integration. Now we consider the variance and the efficiency of plain Monte Carlo. We compute the expectation here. Because xi are independent and identically samples, so we can simplify the function, and we got the answer is just expectation of fx. So it shows that this approximation is an unbiased estimator of fx. And if we apply variance here, we got the answer is 1 over n times variance fx. So it is shown like this estimation gets concentrated around the correct value as n tends to infinity. And since the variance represents the efficiency of an estimator, so if we want this estimator is good, we want the variance of this estimator is small, then how to let the variance small is the question. We consider 2 ways. The first way is choose large n. It always works because we can see here the variance of the approximation is 1 over n times variance fx. So if n is large, the variance will be small. But the problem is if we choose a higher n, we will have a high computational cost. So another way is consider variance reduction method, which I will introduce in the second part of my talk. In this part, I will talk about 2 variance reduction methods. The first one is called antithetic method, and the last one is called contravariate. In antithetic variables, we consider mean of 2 identical but not independent random variables, x and x prime. So we compute the variance of these 2 variables, and we got the answer is here. And these 2 terms, this first term represents the error for standard Monte Carlo, which I introduced before. And the last term here, if this term is negative, then this term means it represents the improvement of our variance, because if it's negative, then this one will be smaller than this one. And for example, to construct x and x prime, we will use inverse transform method. Then we set u is come from uniform distribution from 0 to 1. So we set x equal to f inverse u and x prime equal to f inverse 1 minus u. And since 1 minus u is also distributed uniformly in 0 to 1, so 1 minus u and u have the same distribution. So x and x prime have the same distribution here. And the deadline is let f be increasing, then the covariance of fx and fx prime will smaller or equal to 0. To prove this, we write g of u equal to f and large F inverse u. So we can get fx equal to gu and fx prime equal to g of 1 minus u. And the trick is we consider two random variables u and v, which are all independent and uniformly distributed in 0 to 1. So we can write this in either way. We will got the different sign here and here and here and here. We need this because we will write the expectation of g of u minus g of v times g of 1 minus u minus g of 1 minus v, because these two terms have the different sign. So we got this expectation is smaller or equal to 0 here. And if we extend this equation, we got the answer is 2 times covariance fx prime. So covariance fx prime is smaller or equal to 0 as required. Now we can use the approximation. Since this term is smaller or equal to 0, we know that if we choose this x and x prime, we will have a reduction in variance if we apply anti-static variables here than plain Monte Carlo. So we use approximation like this. We set this yn, and we compute the expectation value of yn, and we found that this will be expectation of fx, which means that yn is an unbiased estimator of fx. And we compute variance of yn, we got these two terms, which means this one is the error for standard Monte Carlo, and this one means the improvement, since we proved that this one is negative, and this is improvement term of the variance y. And the example here is we let fx be x, and x comes from uniform distribution of 0 to 1. So we know the exact value of fx is 1/2. And because large F inverse u is u, so we can write xi equals to ui, and the xi prime equal to 1 minus ui here. Now we put this in yn, we can calculate that yn equal to 1/2, which is exactly the same value as here. So we know that in this case, yn is an unbiased estimator, and it has no variance. And for comparison, we consider plain Monte Carlo method here. It's like this. So we calculate the variance of the approximation of plain Monte Carlo. We found that the answer is 1/24 times n. So this value is larger than 0. So in this case, we consider anti-static variable is useful than plain Monte Carlo. We reduce the variance. And the second method of variance reduction is called control variance. And in this method, we define a new variable called w is equal to x plus beta times 1 minus u, where y is a random variable with a non-mean mu, and beta is a constant. And we can prove that this w is an unbiased estimator of x, since here no matter beta is chosen. And the variance of w is, we can compute, the answer is here. And if these two terms, beta squared times variance y and plus 2 times beta times covariance x and y is negative, then variance w will smaller or equal to variance x, which means that we improve the variance, we reduce the variance if these two terms are negative. Since we can see this equation as a quadratic function of beta, so we compute this equation, and we got it is minimized as beta equal to beta star, where beta star is equal to this minus covariance xy over variance y. So we put this beta star into the equation here. We got the minimum variance is this one. So we can see that the variance of new variable w is reduced by this amount of the variance x. Then this is the value that we reduce the variance, and if we divide this value by the original variance variance x and this term and times 100%, we got the percent of variance reduction. And since we can simplify this, to correlation of x, y squared. So it shows that variance will reduce a large amount if we have a strong correlation between x and y. Means this term is higher, will get a strong reduce in variance. And this is an example. We want to compute this one, the e to the power of u du, and u comes from uniform distribution from 0 to 1. And since this is not a complicated function, we can calculate the exact value directly by integral, and the answer is 1.71828. And however, if we apply plain Monte Carlo approach here, we can get the variance of this is equal to 0.2420351. This is the variance. And if we use control variable here, we choose control variable y equal to u, which comes from uniform distribution 0 to 1. Then we calculate the value by expectation of y is 1/2, and the variance y is 1/12, and the covariance xy is equal to 0.1408591. And by the formula I gave before, we can put in these values in the equation, and we got the beta star is minus 1.690309. So we compute the beta star and we put beta star into the equation. We got the control estimator is w equal to e power of u minus this one, and the amount of reduction in variance is this. We just put the value we calculated before, and we got the answer is 0.238095. So the percent of reduction in variance is this value is 98.37%, which is a larger amount of reduction in variance. And finally is the conclusion. I introduced Monte Carlo integration is a method of calculating the integral if the integral is half of 10. And there are two methods of variance reduction method. The first one is antithetic variables, and the second one is control variable. The example shows like if we choose the variable we need properly, we can get a large amount of variance reduction compared to plain Monte Carlo. And this is my reference. This is the end of my talk. Thank you for listening.
Thank you very much. Okay, thank you. I was thinking that, for example, your antithetical example,
Yeah.
is obviously a very carefully chosen example because you get kind of perfect variance reduction of no variance.
Yes.
In practice, how much variance reduction would you tend to get from antithetical variance on a more realistic example, do you think?
It depends on the example, sure, but I guess it's not much like the example I give, because in the example I give it's an extreme example because we got the exact value immediately. But in a common example, I think it's not be like this, just a part of the variance.
And it's the question that always sort of springs to mind with anything sort of like this, where we use clever ideas to reduce the amount of computation. Of course, computers are getting faster and faster and better all the time.